All right, so now let's look at part C of the example. And so the example in part C I have as following. So for x squared plus 1 over 4x cubed plus 3x minus 5, okay, and to the 6th power dx. All right. So for this problem right here, in my experience, I would choose. How about I'm going to use a different letter here for my viewers to be flexible with the naming a variable. It's just anything outside of x right here. So how about an s right here? Okay, so s equals 4x cubed plus 3x minus 5. So my selection for the substitution is this. And again, it's inside a high power, even though this power is in the denominator. Okay, so at the end of the expression of example 1 right here, you can start putting together all of those experiences you have learned throughout my example 1 right here, and you can start drawing out on your own some good formulation of a good path, even though there's still about anywhere from 7 to 10% of unsuccessful out there. It's just the way how integral works out there is. Okay, so now in that way, my integral immediately becomes something as following. This is 4x cubed plus 1. I did not substitute for that, but in the bottom now it becomes s to the 6th, and the dx is still here. All right, so I know that I still have more to follow through. So now I'm going to need to go back here and try to find a way to substitute the dx away. So ds dx here is going to give me 12x squared okay, and I actually had a typo in my previous step right here. The beginning problem was right. It's just this step I had a little bit of typo. Okay, so plus, and so 12x squared plus 3. Okay, and so now I'm on my way to solve for the dx right here. So ds will equal to, because now we're taking that as a fraction, so 12x squared plus 3 times dx. All that here will equal our ds. And so that means ds in the next step over 12x squared plus 3. Okay, that will equal my dx. Okay, and so now I can use this as a substitution for my dx right here. So now into my problem, my actual problem, this is what I'm going to end up with. 4x squared plus 1 still stays the same over s to the 6th, but dx now can be substituted by ds over 12x squared plus 3. All right, and so now I'm ready to move out to my next board right there. All right, so with that current expression, then I'm now going to have 4x squared plus 1 over s to the 6th multiplied with what I see that now as a 1 over, okay, what I see from my previous step, 1 over 12x squared plus 3 times the ds here. But now I can recognize further that there is a common factor of 3 here in my denominator. So now that means I can do this. 4x squared, and I still haven't found my substitution for that 4x squared plus 1 yet, or at least this thing here is still stuck with the x expression, with the x, the old variable. Okay, times, this is 1 over, how about 3 times factored out, and then the 4x squared plus 1 ds. I mean, look how good that brought for us like that. All right. And so now 4x squared plus 1 will nicely, all of a sudden, I realize it cancels nicely with that. So I don't even need to look for a substitution for that any longer. All right, so now all of a sudden I reduce my expression to, okay, so 1/3 times 1 over s to the 6 ds. And this is also the same as, sometimes I can write it as it's the same as 1 over 3 s to the 6 ds. It's the same like that, or it can also be the same as the integral of ds over 3s to the 6. Many instructors, many textbook writers write this same expression differently. Okay, but you can keep it this way, seeing that 1/3 as a fraction, as a coefficient, and then ignore any of these. We don't have to get them into those. And then, but now primarily you can rewrite this 1 over s to the 6 here as a 1/6 power. So see, I've made I have completely washed away my old variable, and now it's something trivial, because here it's now a 1/3 integral s to the -6 power ds. Now I'm so ready for the final answer. Okay, so as far as the final answer, it's going to become 1/3 s to the, and actually it's a little too rush of me, okay, times s to the -5, but 1 over -5 plus c. Okay, and we definitely never want to forget that. Okay, so that means we're looking at -1 over 15 times s to the -5 plus c. All right, and so we can write things as following: -1 over 15 in parentheses 4x cubed plus 3x minus -5 plus c, and to the, that parentheses here is raised to the -5 power. That's our expression for the final answer. Okay, all right, and now I'm going to introduce let's look at now question D here of our problem. So throughout question A, B, and C, like of this example 1, you can see that it looks like so far I try to show you that experience. And I'm not saying that it's always working, but a lot of times when you see an expression being trapped inside either a high power or inside a root, and doesn't matter if the power or the root is in the denominator or not, you can always take that, you can a lot of times take that expression inside the power or inside the root, and use that for your substitution, as your selected substitution. Okay, and then of course there's still about a 10% chance that your selection of the substitution doesn't work. Try another one. Okay, or because that's up to your creativity. There, up to this point there are still a lot of mysterious integrals out there that still remains a challenge for mathematicians out there. Okay, so it's a long journey learning with this. So how about question D? Another problem right here that worth to bring up. Okay, so how about 2x minus 1, and then 2x squared minus 2x plus 5. It's completely a rational expression. Okay, and dx. And so now I'm going to substitute. So for a problem like this, I don't see any high power. I don't see any roots or anything like that. Just a rational expression. But this is what I'm showing you right here as from my experience. And then you will again, as you put all the different little problems I done on the board here together, you can start formulating into a generalization for them. how about we can call that a z, okay, equal to x squared minus 2x plus 5. I substitute for that. Okay, I substituted for that. Okay, so this is just the whole denominator, but is it really inside of a power? Right now, maybe you don't see that as a power yet. We'll get to that. Okay, but so now immediately doing that, then consequently, after doing that, we will immediately get into 2x minus 1 over z. Okay, and then the dx. And so now I know that I'm going to have to look for a way to substitute for dx. And so I'm going to go back to my substitution point right here, and I'm going to go dz dx to equal, at this point in your experience with taking derivative, and this is 4x minus 2. Okay, and then doing a little more algebra here, I'm looking at dz, okay, to equal 4x minus 2 times dx. And so now I'm going to solve for dx by dividing both sides by that 4x minus 2. And so that gives me dz over 4x minus 2. Okay, and so this will be, and then this will become, see, look at that, dx here. Now, in my work, I found that dx can be substituted by the dz over 4x minus 2. So, let it be that way. So, 2x minus 1 over z, but times, this is a dz over 4x minus 2. All right, so look at what we brought for ourselves. And now look at these two terms in my current denominator here. It has a common factor of 2 right there. Okay, so take note of that as I'm moving on to the next board right here. All right, so in the next space of my board here, I'm going to write that as, see, there's a 2x minus 1 is here over z. I'm going to multiply that. I'm going to rewrite my dz expression as a dz separate out, but 1 over, okay, there's a 2 times 2x minus 1. Right? After I pointed out that I recognize the common factor 2 in my 4x minus 2 like that. Right, so in that way, I can go ahead and cancel out the 2x minus 1. So, and after that cancellation, I no longer have to worry about finding a substitution for that. Okay, so now my expression turns out completely in terms of z here. That means I have completely washed away my old variable. So now it's a 1/2 times 1 over z dz. Okay, it's a coefficient. It's a 1 over z function with dz. Some textbook author writes this as a 1 over 2z dz. Okay, some textbooks write this as the dz over 2z. Okay, but in the end, it's a constant coefficient here, and it's just none of these is getting away from that understanding that dz is related to all of these guys as a product. Okay, but then we don't need that here. Just a reminder for anyone. And then in that way, I'm going to keep the coefficient 1/2 here, and that's just, we mainly going to have to worry about the antiderivative or the indefinite integral of that, which is something very trivial. See, for that question, did I make my integral any more trivial after this substitution? I did, obviously. Okay, so the answer at the end now, and this is just a matter of how much you remember from your from the lecture that I deliver about this specific the function right here. It is going to be just natural log of absolute value z, and of course there's that coefficient 1/2 in front. Okay, and then plus c. Do not put this as a z to the -1 power and apply the power rule, because remember, recall for yourself that the power rule has an exception. It works anywhere else except for power -1, which is exactly this case right here. So this is our solution for that. We turn that into the natural log of an absolute value of z right there. Okay, so, and we can't leave a final answer in terms of z. So 1/2 natural log of our original substitution is still here. This is the original substitution. And so in that way, now I'm looking at, I didn't leave enough space for myself to write, so 1/2 natural log 2x squared, absolute value of 2x squared minus 2x plus 5. Outside of that, plus c. We made another problem. Okay, and that is for this particular problem right here. So, as I keep saying, I try to recommend that understanding that anytime you see an expression inside of the power, but in this problem, where is that power? Because I obviously chose this in the denominator as my substitution. But how does that violate what I'm trying to share, the experience I'm trying to share with my students? Of course, there's always exceptions out there, but it's not really violating what I've been sharing, because I see this as a power 1. We didn't need to write it down, but it was a power 1 like that. So it was still some large expression being inside a power. Okay, and then that was the power in the denominator. Just like some of the root problem you have seen earlier, it was an expression inside a root, and that root was in the denominator. And so feel free to try. And if it works, it worked. Bingo, we got the answer. If it didn't, try another one. That's why I keep saying there are always about a 10% of chance that no matter how hard we try, the integral is still unsuccessful. Okay, all right, and so now, but of course, again, look on the bright side, as I have also mentioned earlier, many problems that are introduced. If you are taking a calculus course, then many problems introduced there will be a problem where they're all within your reach. So it's just all about a matter of practicing. Or in other words, I'm saying that we're mostly exposed to common problems, okay? And those are exceptional problems, about a 10% chance of those that you run into exceptional problems. It got to be on to wait for some, the very rare occasions like that where you challenge somebody else or something like that. Okay, and then so in that way, let's look at another one for here, and we're about almost done with example 1 right now. And of course, I just decided to deliver the more examples the better, but if you feel like you're already comfortable, go ahead and fast forward to my next example, where I introduce a different class of problem where we can use a substitution rule again. Okay, and so now part E of this example. Sometimes, surprisingly, a problem as simple as this can get students of mine hung up, so I decided to deliver that in this lesson here. So 5, a constant, okay, and then over 4x plus 3, something like that. Basically, it's a constant over a linear. That's what I'm trying to explain. So that's the generality of this problem right there. It's just 5 over a linear. And so in that way, I want you to take this problem very similar approach with the problem I have done in part D right there. So that means my substitution u is going to be just that whole denominator, 4x plus 3. 4x plus 3. Because the way I see it, this is some expression inside of a power 1 like that. Okay? And so now that means I can start putting the pieces in place right here. 5 remains the same. The denominator here is substituted by u. The dx didn't get a substitution, and that's why we're on our way for it. Okay? And so now du dx equals 4, the derivative of u as a function of x. Okay? And then that means du equals 4 dx. And that means further that du over 4 equals dx. All right. So now this is our substitution that we made. This is what we picked. This is what we produced. And we substitute that into the dx here. And so now I'm looking at, or maybe let's save space here. So integral of 5 over u times du over 4. Okay, that's the problem we ended up with. So we at this point have completely washed away the old variable. Okay, the old variable, and then so now is this something that we can move on trivially? Yes, we can rearrange the 4 in the denominator to the same fraction here, and it will become something like this. We have what we're looking at here is a 5/4 times 1 over u times du. And so for this one, I don't think I need to even advance to the other board again. This is a coefficient, and so 5/4 can be pulled outside because it's a coefficient, and it's a 1 over u du. And so this is now just like in part D that we have done. Like that. It's going to give me a 5/4 natural log of u, but put u in absolute value for me. Okay, plus c. And then so the final answer cannot be in terms of u. So we have to bring the old variable back. So 5/4 natural log of now 4x plus 3 in absolute value plus c. But this is, ladies and gentlemen, our final answer for that. Okay. So 5 problems that I introduced in this example. I purposely brought up one common class of problems where you can it brings you into some good experience of what could be a good choice, who could be which expressions among all of these crazy expressions can be a good candidates for being substituted away. Okay, and so in that way, to go ahead and practice on your own, and then anytime you're feeling comfortable, you can advance to my video right there, and then let's check out example 2. All right, so now I'm going to introduce a different class of problems, where in this class of problems, so in my style of creating examples, each example is a class of problems. So each problem in the particular example has some similarity with the other problems in the same example. So part A, B, and C, they're all having something alike right there. So as you're studying along with me, you will recognize that style, how I design my examples. Like that. All right, so part A of my example 2, and maybe to get some. All right. Okay, so how about integral of 4 dx over x with a natural log of x to the 5th power. Okay? And so this one here, and again, throughout the lesson here, I keep mentioning that I had a different video where I explained the importance of the dx right here and how you should understand about that. So this is one case right here where you can see that the problem started out because I found this problem in some of the textbook, and in quite so many textbooks out there actually, and the way it's written like this. But what you need to understand now is that it's really a fraction over this, and you can also rewrite this as a 4 over x times ln of x to the 5th, and keep the dx separate because it's all in the inner product. So you can put it all together in a fraction like this or separate out. Okay, that's different choice like that. But maybe keeping it like this is a little easier. But now as far as the substitution, I recommend substituting the natural log, not that one, the natural log of x inside of the power, not the whole natural log of x to the 5th power. And so u equals natural log of x. That expression inside of the power, and the power is in the denominator, but it shouldn't matter. The point is it's a logarithm inside of a power. And so it works a lot of time. And again, I never said throughout my video here that what I'm showing you here is absolutely the only methods that works 100% of time. No, there are always about a room for some creativity out there that you need to be thinking outside of the box. Okay, so there are always some exceptions out there. But this one right here, you can rely on my experience. And so after making this a substitution, we can go for how about, I'm gonna That's du dx, okay, equals 1 over x. That's just the derivative. And so solving for dx, du equals dx over x. Okay, and now I have said many times in this video lesson, it's all due to the fact that now we are allowed to think of this expression as a fraction, one expression du over the expression dx, like that. And so now I can solve for dx in terms of du, so multiplying x to the other side. So x times du equals dx. And I can use that as an expression to substitute for my dx here. So now we are ready for this. My substitution, my problem here, 4 didn't get a substitution. It stays the same. This x did not get a substitution. It stays the same. This natural log of x has now become a u to the 5th power. And the dx here is substituted by x times du. Okay. And so now the worry about not finding a substitution for x is gone because we can cancel that away. And so now my problem simplified down to 4 over u to the 5th du. And look at how trivial it is. Okay, it started out being something that first sight, when I was a student myself looking at this thing for the first time, it really scared me out. But as I went through and learned patiently from my professor back then, I made my way up. Okay, so I want that same experience to be passed on to anyone learning from this video lesson right here. Okay, so that same way, this thing now can be turned into about one more extra step right here, 4 and u to the negative 5 power. How's that? Okay, and that's why I keep saying it's so trivial now. It's an integral that's so trivial to see the answer. So 4 times 1 over negative 4, because that's coming out from the power rule, u to the negative 4 power, even though I almost wrote negative 5, okay, and plus c. And then again, we can't leave the final answer in terms of u right there. And we can also cancel out that those 4s. So now I'm ready for my other board right there. So now my answer is going to be negative u to the negative 4 plus c, and that is the same as minus natural log of x to the negative 4 plus c. That's the answer. Or alternatively, you can rewrite it as a negative 1 over natural log of x to the 4th power plus c. Two different ways. If this would be a natural class, any of my students, I welcome any of these two different answers. Okay? All right. And so, same example. But now let me bring in another one to again enforce my experience with for any one of you. But still, in the end, that's not the only way. Okay? You are still more than welcome to explore about different your own creativity out there for these kind of problems. All right, so it's an integral problem for about 5, and then in parentheses, natural log of x to the 4th power over 4. Over x dx. Okay, and so with this problem, again, very similar arguments, very similar reasoning with my earlier problem. I see there's a logarithm, a natural log specifically, being trapped inside a power. But this time it's not, so being in the denominator or in the numerator like this, it's not the necessary factor here, but being a natural log, in general being a log inside of a power. That's what we're going to tackle immediately. But that's just my experience. It works with me. But I'm not, as I've been saying, I'm not stopping anyone from creating your own path like that. And who knows, you got more victory than me. Okay? So natural log of x And so du dx equals 1 over x. Okay, and so solving for this, we're looking at du equals dx over x, or, and I misspelled that, dx over x. So the same way as it's the same algebraically as x times the du to equal dx. All right, and so now into the expression. Now we can start putting the pieces together. Okay, so it seems like I'm going a little bit out of the order that I've been going through in example 1, but believe me, when you become fluent enough with these problems, you can carry out a problem in whichever order you would like to, but it will land you into the right answer. Okay, so the truth is just the truth. And so now 5 times u to the 4th, because that's what was chosen to be substituted for, and divided by x. Sadly, we didn't have a substitution for this. dx, we made a substitution for that, so it became x du, all multiplication. And so now we found a good usefulness here. We can cancel the x away, and without worrying about later on finding a substitution for that. So now we are permanently left with 5 u to the 4th du. And is this, ask yourself this question, is this a trivial integral to carry on? Yes, it is so trivial. So the answer now has to be, it's going to be u to the 5th plus c. Okay, and we just simply can't stop at the final answer with the answer in terms of u, so we have to bring back what that was. So natural log of x to the 5th power plus c. That's our final answer. And really at this point, this completes my example number 2 right there. All right. So now let's look at example 3. A different class of problems again. All right. And so how about now I want to introduce an integral that has about 4x minus 4, okay, in parentheses, and multiply with e to the x squared minus 2x plus 1 dx. Okay. So it's an exponential function involved here, but then in the exponents part of that, it's a lot more than just x, because exponential functions start out with the simple one, e to the x, but now we're not just simply having e to the x, we're having e to the x squared minus 2x plus 1 and all that. Okay, and so again, as experience of mine, that's throughout years of doing this, I see it usually works. Okay, it usually works that we tackle down, we pick that expression right inside of, because the part that stays in our exponents in the exponential function, that's a lot of time I call it, it's some expression being inside of another one. The outside function is the e to the something, and then all of that there, x squared minus 2x plus 1 is being seen as being inside of that exponential function. Okay. And so in that way, I'm going to substitute. But in the end, it's just an experience, and it worked for me. So now I want to show that to anyone. U equal x squared minus 2x plus 1. Okay? And so that's my choice for the substitution. And so as I did this time, let me go back to the certain that order I did in example 1 right there. 4x minus 4 did not get any substitution. It can stay the same. All this here, e, now can significantly be reduced, e to the u. Okay, and then the dx is still the being hung up here. So I'm going to get back there and find a good substitution for that. So du dx is 2x minus 2. Okay, du dx is 2x minus 2. And so in that way, I can see that du equals 2x minus 2 times d dx. and I can divide both sides by 2x minus 2, so that gives me du over 2x minus 2 equals dx. All right, and so in that way, now this is what I see it. 4x minus 4, okay, times e to the u times du over 2x minus 2. Why did I do that? Or what allowed me to do that? Because this dx equals all that here. Now I can use that as a substitution that I've made for this dx right here. Okay? And so now let me advance to the other board right here. Right now I'm running a little short of space here, so all right, so moving on to my next step. This time allow me to rearrange my current expression as following. How about I'm going to write that 4x minus 4, and you got so many ways of writing it. And being on the board up here to show my students how to approach the problem, I choose slightly different route each time to catch my students' attention. So all that 2x minus 2, I'm going to put it right underneath that 4x minus 4 in one fraction. And then there's e to the u, and then there's that du. That same expression that I added up there is now here. That's what it is. Okay? So what's good about this? See, it's just this one, this expression is just the double of that. So you can think about canceling this out and have a 2 left. Okay? So now my expression in the next step turns out to be just simply 2 e to the u du. All right, 2 e to the u du. And now this is a very trivial integral already. All we do is just jump into the next answer. That's right at our answer. So 2 times e to the u plus c. That's how we take that's how we integrate e to the u function or e to the x function in general. And this is just a constant coefficient. Okay, and now we just can't stop with the answer in terms of u. So 2 times e to the, what did we substitute for? We substituted x squared minus 2x plus 1. Okay, and so in that way, let's continue. X squared minus 2x plus 1. Okay, this is our final answer. All right, this is our final answer. And we've made it. Okay, so that's another kind of problem where now you are exposed to exponential function, and your exponential function has some exponents that's a lot more than just e to the x. And so in that way, good experience I've been doing in my past that just tackle right into that expression in your exponential function, and it will work a lot of times for you. Okay, and so same example. Now, when we're talking along with that along the way about the exponential function, now I want to come back to something that I have taught back in that video lesson about how to find antiderivative. But at that time there, when I was giving that lecture about taking antiderivative, I only introduced that as something to remember, something easy enough to remember. But now in math, there's nothing to remember. You got to know how to derive it and how to make reason for it. Okay? And so let me bring up this little example, and you will understand my intention. So how about find the antiderivative, or just integrate, take the indefinite integral for e to the ax dx. And again, this is the reason why I had that video outside of this lesson about how important it is to indicate the d expression with the variable consistent with the main variable of our problem like this. See, because here we got a lot of letters. There's the e letter, everybody knows by heart that it's an exponential constant. But a here is a letter. It could be any value. And x here is also another letter. It could be any value. And so the dx here is making it clear for us that in this entire expression, x is the variable, but anything else either is a constant or a constant coefficient. And so in this case, it looks like it's the way how the expression looks is a times x. But x is the main variable, so a has to be a coefficient in front of that x. Okay? And so now as a reminder, if you pause the video now and search for that other video where I first introduced about the antiderivative, then this answer would be exactly 1 over a. This is what I explained there in that video. 1 over a times e to the ax plus c. End of story. And I told you it's just one of the special rules to remember, special enough that it will stay as you work often enough with that. But now, as I said, we're math people. We don't want to take something that's just something to remember. No, it's not good that way. So here's how it works. It waited all the way until substitution rule to get things really clarified out. Okay, so this is how I see it. In that same experience I've had with that earlier example, part A, earlier question in the same example, I can now make a substitution. How about let's call that z equals ax. Keep in mind for yourself that a is a constant coefficient and x is the main variable. So dz dx is just simply a. Simple derivative rule can land us into that. That means dz will equal a times dx. Or one more step, dx can be expressed as dz over a. These are all just the algebraic manipulation of that important step right here, finding the derivative of your z equals ax. But now, how does that work in this problem? E to the ax. Ax is now substituted by z, so e to the z. Okay, there's no other extra expression except for that dx. But dx now is substituted by, or can be substituted by dz over a. So dz over a. Okay, and so now I can see this as really 1 over a times e to the z dz. Okay, and so my final answer is here. 1 over a times e to the z, okay, plus c. That's my antiderivative for that. But this antiderivative should not be like this because we were starting out with a function in terms of x. So I'm going to bring back that original 1 over a times e to the ax, substituted back in z right here, plus c. Does this agree with what I have mentioned before as a little special rule to remember? But now it's here. Okay? All right, so now at this point, after 3 examples back to back, we are ready to concern about, so what about when it is a definite integral? Because so far, 3 examples and a lot of little sub-problems in those 3 examples, I've done mostly on the indefinite integrals and mainly just antiderivative. So what about when we really are for a definite integral? Okay, so I'll put that question of mine here. What about definite integral? What about definite integral? Okay, what you are waiting for is here. Okay, so let me introduce a demonstration problem. It's not even an example yet. Okay, so I'm going to do a demonstration. So how about x times square root of x squared plus 1 dx. And now I want to go from 0 to 1. Okay, I'm going to step quickly to the other board to erase it out. All right, so hopefully after 3 examples with a lot of sub-problems in it, and you are fluent enough with the idea now at least, then at least this is what I can start out with. So in the experience I've been doing, then I'm going to pick a substitution. I'm going to pick a substitution, an expression to be substituted away. So how about this? X squared plus 1. So that's why I'm saying how about, because somebody else can pick something else. So how about x squared plus 1 to be substituted with u? And so that means my expression, but keep in mind the goal now. Once I made a substitution and decided new letter name, then that means I want everything else is in terms of the new variable. See, that's why there was a question about, did I completely wash away the old variable? Okay, stay very close with that philosophy of mine right there. Okay, and so that means on the way of the work here, the integral sign, x didn't get a substitution yet. It's still here. And how about, let me do this so that you don't really have to do that, but for teaching purpose, I'll do this so that to remind you that whichever didn't have a, so in this step right here, I only substitute u. So whichever else didn't get a substitution, I'm going to write it in red ink. How's that? So with red ink, the x here is going to be written in red ink. The dx for now, I didn't find the substitution for that yet. I'm going to write it in red ink. Even the two limits here of our definite integral here, they are the values that in respect to x. Low x, high x, low x, high x. I'm using that term right there. So 0 and 1. But start thinking about my intention. I even include these with red ink. That means there's something I'm going to have to handle with them. Okay? But then at least the square root operation now gets substituted away. So that's square root of u. So we still have a lot to go. Okay? So let's handle that as usual. So du dx is 2x. Okay? And hopefully anyone can agree with me easily on that. So that means du equals 2x times dx, because now we're treating du dx as a fraction. Okay? And that means further that I just see, and it's always, you can see my style that over years, ever since I was still a student, from the first day learning about this method, I have been forming for myself into that habit about, all the work on the u method, on the u substitution, on the substitution here, I keep them in a separate space. And then the work where I start putting in all the substitution details into the problem, it's in the continuation. It's in the continuing steps of the problem right there. Okay? And now this workaround is going to be a du over 2x to be equal for dx. So now I found a good substitution for dx. All right, so my next step should appear as following. And still the same way I'm doing. Whichever else still didn't get a substitution, I'm going to leave that in red ink. Okay? So the integral, of course, well, integral doesn't need red ink. The x is here. Okay? Square root of u. And so now dx becomes a du over 2x. And then these two limits, that's what's starting to worry me. They still remain red. Okay? Now that red x right here now is ready to be cancelled away. Okay? With that x in the denominator, just as the work you've been seeing. And so now I'm going to go ahead and cancel the x away. Okay? And so now in my next step, this is what my integral becomes. And still, again, I'm still writing red ink for whatever is needed to still be substituted away. Whatever is still needed to be substituted away. 0 and 1. Okay? Provided that now we cancel the x away, then your expression now becomes 1 over 2 square root of u du. I write these two in red ink because really these also need to be substituted away, because the values right now are in respect to the x variable. So if you plan to plug it in, you have to plug it into the x variable. You can take these values and plug it into u at the end. Because at this point, anyone learning about this lesson is pretty much fluent with the fundamental theorem of calculus. So eventually, so you know that eventually you will have to take the antiderivative of this and then plug value in, right? Plug values in, high going in first, and low going in after, and subtract out. But we can't plug these two values in because they are red. They need to be converted into the values corresponding to the u variable. That's the point right there. Okay? And so, now I'm going to go back to my earlier board. This little space left on my board here, we can do something else. Because I chose, see? There's no right or wrong about what we chose for a substitution, but because we chose that, it's going to start producing consequences. So because I chose u equal x squared plus 1, and so now, okay, end of the little story here, when x equals 0, it gives me, how about I'm going to call it u1, the low value of u. Okay, u1 is just the low value of u. It's going to be 0 squared plus 1. What did I do there? I substitute the lower limits in respect to the x variable into the substituted into the expression of substitutions right here. So x squared plus 1, I'm going to substitute x equals 0 into that substitution expression. And so I get 1. Okay, so now, sorry for the switching back and forth right here, but I hope that's interactive enough for people to catch. This now, actually I still keep that in red ink. In the next step, 1 by 1, this still remain 1 here, but that now is legally 1. So it went from a 0 in respect to the x variable, but now in terms of the u variable, that's supposed to go with 1. And then 1/2 square root of u du. Okay, now we have one more red ink thing to take care of. All right, so just like that, when x equals 1, where did this 1 come from? Our upper limits of the definite integral. Okay. When we substitute that into the expression right here, it leads to, how about I'm going to call, it's just a tradition, and it's been working, so I stay with that. Many of my past professors use that. u1 is for low limits when we substitute it, and u2 is for the upper limits after we substitute it away. So that gives me 1 squared plus 1, which is total to 2. Okay, so in that way, now in my next step, my integral finally becomes, see, 1 is the bottom, 2 is the high. 1/2 square root of u du. Okay, is this integral trivial? Yes. Okay, so are we ready for getting the final answer? Yes. Let's go ahead and find the antiderivative of this. Well, this is u to the 1/2 power, right? So fundamental theorem of calculus, say 1/2 times, let's say 1 over 3/2 power times u to the 3/2. And the instruction says in the next step, of course, we're going to plug in some values, right? As everyone already noted, not 0 and 1 here, not 0 and 1. And as a matter of fact, don't go back with 0 and 1 because that's what we did. We already turned everything into something into the expressions and values that are relative to or in respect to the new variable u. Okay, and so in that way, this is from 1 to 2. That's what my argument is. Okay, and so now this will cancel out and give me a total of 1/3 u to the, it's the same as 1/3 u to the 3/2. So that we can eventually substitute in 2 and 1. Okay, so now it's going to be 2 to the 3/2 power over 3 minus 1 to the 3/2 power over 3. Okay, and then I can see that this value here is not so rational. It's a very irrational value, so we can leave that the same way it is. Or if anyone is having a calculator, you can pull it out and get decimals. But that's not the point. The point now is that when you are, and so now the idea I'm about, and sorry for kind of cutting out in the middle, but the point is, once you have been fluent with how to find the how to use the substitution method on the antiderivative in general, then getting onto the definite integral is just one extra step. Everything remains exactly the same. All that work structure remains exactly the same, except for on top of that, you go one extra step. Change your integral limits into those values that's corresponding to your new variable, your whatever the new variable. So here I chose u, so these are corresponding to u variable. Okay. So I have to point out a couple mistakes like this that I commonly see in my students, and I'm trying to avoid. Also, there are students who argue with me face to face that what's wrong with that, but it will be wrong at some point. So this is what my former students did when classes were still back to back. I mean, face to face, and we still have that instructor to students interaction. Okay, so on the same problem. On the same problem, it was from 0 to 1. Okay, that was the original. So the whole idea is we never have to go back to the x variable anymore. That's the whole. Also another whole idea about that. After we change everything, when we are doing the substitution method on the definite integral, we never have to go back to the old variable x anymore. We just went on and get straight into the fundamental theorem of calculus. And so that kind of created a controversy. I mean, some kind of informal debate that went on forever between me and my students. Maybe because I was too easy some point about not making it's like a strict rules or anything like that. But I keep having students trying to debate with me or making arguments with me as following. Why not? Why can't I just do this? Well, everything like I did right there, u equals x squared plus 1, and so etc. We came down to du over 2x, and then equal dx. Okay, and all that there, but entirely skip that work. And so just still leaving the 0 and 1 here and turn the whole problem into see all that substitution going in, and it's a 1/2. It's a 1/2. What did I do there? So square root of u du. So students just refused to change these values into the new values corresponding to the new variable. And they argue with me that they can just remember these in their mind that these are not for the u variable. So that they keep going on. So that means in the next step they're doing this. It's a 1/2 times 1 over 3/2 as the standard antiderivative work. Okay, and then evaluating all that. They still writing this symbol there. They still writing that. It's a scary sign right there. And then they promised me that they will remind themselves to bring back the x variable. So and of course these cancel out to become a 1/3, and they promised me that they would bring back the x variable like this, okay, to the 3/2 power to successfully substitute in the two values here. So now if they're doing that, then it's fine. They do it. If they did that, it's fine. But trust me, eventually in real practical situation, there have already been a good noticeable number of students. They promised they would do that. But in the end, at some point, you could be taking a test, you could be taking an exam, you could be in a situation that you're doing the problem in a rush. You forgot that this is for x, and you forgot to bring back the x variable here. So consequently, the bad thing was many of those students of mine, they plugged directly these values, which is not meant for you, but they plugged in directly into the u variable, which was way off the hook right there. Okay, so if it was my student, I mean, if that argument keep happening, then I have nothing else to say. But if you really have to go that way, then you're on your own risk. Okay, but I highly recommend anyone learning from this video lesson, I highly recommend not to go on that path. It's a very dangerous path. Okay, very dangerous. It leads yourself into an answer that's completely off the hook a lot of time. Okay, and so now something like this is okay, but it's longer, and you can already see that. See, it's already longer. I mean, why do you have to keep permanently doing this, and then at the end you have to bring back the x and then put that in? it's already longer. You can just do a quick little math here for these two values, and then from here, fundamental theorem of calculus can come in immediately with the new values. Okay, and that's not to mention that there are professors out there who are strict about this. They just can't logically accept that if you change the new variables, then you can't use the old values to match up with the new variables. There are professors who are strict on that. So I mean, maybe I'm easy, but other professors who know, they will pick you on that. Okay. All right. So now that's one thing to discuss. One common thing to point out. Now, you can do the following. You can just start out the problem completely as an antiderivative. You can start out with this. Completely, as I said, completely as an antiderivative, meaning skipping the two limits there. That's completely legal. And you do your substitution thing, okay? And you end up as an antiderivative, being okay, so that was a 1/3, right? And u to the 3/2 plus c. That's your antiderivative. And then you're going to make the next line. That this will imply that the definite integral version x square root x squared plus 1 dx. This is logically correct right here. But in the end, it's still long. It's still more steps. It's equal to this antiderivative 1/3 u to the 3/2 evaluating in 0 and 1. Doing it this way, then you can stay with the old limits values the whole time. Okay, with no one being unhappy about that. But as far as the amount of work, you make it longer for yourself. Okay, so that's how we are doing doing the substitution rule or the substitution method on a definite integral. Okay, so after that thorough demo right there, hopefully explains enough details right there. Then let's look at some examples. And now we don't need to have as many examples anymore, because believe me, you have seen enough ideas right there. All right, so now to continue with our current lecture here, then I'm going to call this example 4. But this is all about the definite integrals. Let's evaluate. All right, so how about part A? Let's look at the problem as following. The integral from 0 to 1, x times e to the x squared dx. Okay. And so now with that problem, I'm going to spend some time finding the substitutions. So just like that experience you have seen earlier, the expression inside of my exponent of the exponential function here, well, we can give it a try, because it's a good experience that this teacher has done that through, so why not? You can try again, right? So we can try, so u equal x squared. Okay, so du will equal 2x. Du dx, and so that means du itself, as we solve for that, is 2x dx. Okay, and so now that means du over 2x will equal dx. All right. And so now I'm going to still have a little more to go. Just like in the experience I've had earlier, have I substitute everything? Nope, not these two limits this time. And so I'm going to have to say, how about u1, which is the low value for u? I'm going to go with the 0 squared, because 0 was the lower limits for x. now substitute it into the substitution expression. Then that's 0 squared. So my u1 is the 0. u2 value is the upper limits for the u variable. So 1 substituted into this, and that gives me 1 squared, and that will equal 1 as well. And so sometimes the integral turns out looking almost alike, but it doesn't always mean the same. It doesn't really mean the same. So now, as an integral, as a definite integral, then there's x here that didn't get a substitution for, e to the u, because x squared is substituted by u. dx is substituted by du over 2x. And the two limits here looking like the beginning two limits, but they're already been changed to be in respect to the new variable u right here. So 0 to 1. Okay, and so now, in this problem, you can see clearly that we can cancel the x away, so no more worry about the x. We have successfully washed away or completely washed away the old variable, including these are actual values. It's now completely in terms of the new variable. Okay, e to the u du, and it's actually a 1/2. All right, and so now I am looking at 1/2 e to the u. I don't need to go back to the x variable anymore ever, 0 to 1, or to be substituted in. All right, so look at how easy this is. It's going to be, so 1/2 e to the first power according to the fundamental theorem of calculus, minus 1/2 e to the 0. E to the 0 is 1, and this is just e, so it's really just, okay. So my final answer is just really, how about e minus 1 over 2, okay? And it's just me that anytime it comes to the expression that involves e, I want to leave that all in exact expression like that instead of going with decimals. Okay. All right. So that's how we carry out that's how we apply substitution method, the substitution method into a definite integral problem. So let's look at one more problem in this current example, and that should be good for our lesson here. All right, so the last one I have in this example. All right, so how about an integral from -1 to 1, x times x squared plus 3 all squared dx. Okay, and so now in this case right here, in this particular problem, once again, you see I have an expression inside a high power. So I can still utilize that same experience of mine to see how successful we can be with that. And it's been working for so many years with me. So let's try it again. And if it doesn't work, we're going to try exploring a different option. So u equal x squared plus 3. Okay, u equal x squared plus 3. All right. And so now with that, then this is going to become, it gives me du dx equals 2x. Okay, and my du will equals 2x dx, and solving both sides for dx right here, solving for dx, we're looking at du over 2x to equal dx. All right, and so now one by one I'm going to put all the pieces here together, and I also forgot to substitute the values for the two ends right here. So u1 is going to be -1 squared plus 3, which gives me a 4. Okay, u2 is a +1 all squared plus 3, okay, equals 4. as well. Okay, and so now we are ready for substituting it. Lower end becomes 4, upper end becomes 4 again. Okay, and then there's x, and now because x didn't get any substitution for that, we got u square, and then dx here becomes, what do we have here? du over 2x. And so again, the x here will cancel with that x. We're looking at the final expression here. 1/2 u squared du, integrating from 4 to 4. Integrating from 4 to 4. Okay? And now it may look a little bit shocked for anyone to see how this the lower end and the upper end has equal value, but just follow the fundamental theorem of calculus. You will be surprised. Okay? You will be amazed how that fundamental theorem of calculus will work for you. What I did here, which is simply, once again, once I decided to change the variable, you see the substitution method now at ultimately almost at the very end of our lesson, there was an ancient name of this substitution method. They call that the change of variable method. Okay? Because when we substitute away, we change the name of one expression to another variable, and then consequently we completely, see, I said we washed away completely the old variable. That's why, I mean, I learned, I formulated myself into that style of checking myself like that, because there was a time I read a little more advanced calculus textbook and some of the old-fashioned calculus textbook, and they call this method back then the change of variable method right there. Okay, and when any one of you advance to a higher course where you investigate calculus in a much more in-depth understanding than this same method right here, yes, people there will call that the change of variable method as well. Okay, but that's a long story from now on. So here in these common calculus courses, we call them the substitution method. But so once we change the variable u right here, then the fundamental theorem of calculus still work, and all the proper work and the steps have been done. So now I'm going to look at, so this is going to be a 1/6 u cube. Okay, allow me to start speeding up the process and assume that, assuming that you're all already fluent with all that taking antiderivative steps. So now I'm going to substitute in 4 and 4. Okay, and so needless to say, see, this is what we have right here. 1/6 times 4 cubed for upper end minus 1/6 times 4 cubed for the lower end, and so the answer turns out consequently 0. The answer turns out consequently 0. Okay, so this is how we follow. We did not do anything wrong with the method. The answer really is 0. I mean, if you don't trust yourself in this, you can hop onto internet in these days, go Wolfram Alpha. They have a pretty powerful built-in integrator. It's a machine that does integration. You have to understand that these math we're learning in these days are so common to the point that people can even program it, okay, for machines to do these things. Okay, the reason I mentioned this, I'm not opening a door for any one of you to let the machine answer the work for you, but I want you to understand that you got to keep working and so that you are the master of your machine, instead of letting your machine, something that's meant to be your slave, to take over your priority right there. Okay, but so this can be handled directly by machine, but machine has a different algorithm to handle that, but it will also give you a 0 answer right from there. Okay, or you can try the Desmos.com that I've been using throughout a lot of my demonstrations. All right, and so now we're done with everything we need to know, everything that you need to know. I feel that I've had enough detailed explanations. So now, before I completely move out of this lesson here, I just want to have a reminder again that, so let me now pick any of the random problem that we've done. Essentially all of the antiderivative problems, because I forgot one fact. So now let me conclude my lesson with reminding you with that fact right here. Because also, the internet in these days, it's a very good resource, but it can also be dangerous. I mean, I have to post my lectures on the internet, but it's also a place where if you don't know how to filter out the correct information, you you might be led into the incorrect path easily. And so you have to understand that the only way to check whether you have found the correct antiderivative is to take the derivative. And so I highly recommend start doing that right after you view this video lesson and successfully learn that skill, because there will be a lot of people over the web. They will suggest a lot of different kinds of answers and different kind of formulas and shortcuts and all that for all of these rules right here, and they come up with all kinds of answers. So if you want to understand among all of those which one gives you the correct answer, because sometimes you are in the desperate situation that your direct instructor here is not available immediately to help you out, and you're completely on your own, then you have to know that throughout all the helping resources out there, you have one way to always tell whether they have given you the correct answer or not. Take the derivative. If they give you something that you're not able to take the derivative of, something's not right with that answer. Okay? And so, and I don't mean that you're not trusting anyone trying to help you out, but it's a way that you can verify for yourself right there. So let me bring back that example we've done here. How about this example? 4x minus 4 e to the x squared minus 2x plus 1 dx. I'm not going to go through the whole example anymore. This was example 3, okay, part A. We went all the way through, and our final answer was, I almost have to calculate the whole thing from scratch here, but that should be the e to the x squared minus 2x plus 1 with a 2 in front, okay, plus c. That's our answer. That's what we've had. And of course, I did not even, the reason it took me a little while, because I did not write the answers here. I only wrote down the problem to prepare, and I worked instantly on the board to show anyone. And so now, how can I tell if I did not make any any mathematical errors in between the steps here? Because the method is solid, well proven, but who knows, we're human error. We are human beings. We make mistakes all the time. I make mistakes too, even throughout my video lecture recording here all over. My students recognize my errors all over. I'm just a human being like anybody else. So here's how you can do it. For this particular kind of problem, take the derivative, okay? So now if you believe that you've come to the final answer, spend a little time. Even if your instructor, whoever that is, does not require, spend a little time, take the derivative to verify that you have done the correct work. You don't want all your lengthy work and in the end got to your instructor and got docked off for just some minor error, and then it led to an incorrect answer. So in that way, two terms. Constant term here, taking the derivative gives me 0. So primarily it's this term right here. Coefficient stays the same. Outside function is the e to the something. Inside function is an x squared minus 2x plus 1. And so in that way, I'm looking at what? I'm looking at e to the x squared minus 2x plus 1. That's the derivative of the outside. It stays exactly the same. Chain rule says I'm going to multiply with the derivative of the inside here. Okay, so that gives me 2x minus 2. Okay, and I never have to worry about the constant c here because it's taking the derivative on that. It's 0. And so now 2 times 2x minus 2, it leads me to 4x minus 4. And then multiply with e to all that x squared minus 2x plus 1. Does this look just like the beginning function right there in our integral problem? And yes, it does. So now you know that you have found the correct answer. All right.